Okay, so first things first, let's kind of introduce ourselves to what machine learning is. What is machine learning and what is this tool in and of itself? Well, what it is say you have some input up here. Take whatever information you want to drop into this box up here and basically feed it through a feed-forward network and get some machine learning responses out on the other side. And what these responses are the classes 0 through 9. So one of the first things that you do whenever you're getting ready to say you want to learn a new programming language is you learn the hello world. Well, the hello world of programming, of machine learning is basically, how can I see the numbers 0 through 9? Well, let's see what we can do. If I put the number 0 inside of here, what does it get? Well, apparently all these blue and black and kind of varying color things. There's this view that we have right over here, which goes up into this next level. And then we go over to here, and clearly it looks like 0 is the most blue or the highest color. If we look over here, it downsamples it. It says that it looks like this. The first guess is a 0. The next guess is a 7. So its first guess is correct. Okay, how did this work? What just happened? Like all we have here is a whole bunch of numbers, or we have like a whole bunch of like colorful blocks. What the heck is going on here? Well, first things first, what is this? This first layer is basically a flattened version of the layer below it. So if you imagine this right here as being 26 by 26 pixels, or maybe it was 27 by 27. I think it was 27 by 27. Yeah, 27 by 27, sorry, 27 by 27 pixels. Then what you get is the result of 729 pixels. If you were to, feel free to do this if you really want to, if you were to count every single one of the pixels or objects inside of this line right over here, this bottom one, that would equal 729. Because literally what's happening is it's taking this two-dimensional image, this flat picture, and it's taking it and it's making a long one-dimensional representation of it. From that long one-dimensional representation, we're actually learning a much smaller representation. And that much smaller representation, is what then goes ahead and informs our actual answer. So this concept, what we just talked about right there, the idea of basically taking something, flattening it, maybe reshaping it is a better word. So taking an idea, taking an object, reshaping it, and then doing math to it. So in this case, the math that we did is we took an object that was flattened and we shrunk it down even smaller. And we can talk about what that math is, but without going too deep into it, we did some math to it. And then we did that math one more time. And by doing this 2 times, because this first one is just our input, this layer right here is basically just a flattened version. So we don't really do much here. But we do our math once, we do our math twice. In doing that math 2 times, somehow we went from a picture of this wiggly 0 to us knowing that the machine learning, that the computer has a 0 entered in. So let's go a little bit farther. What about if we enter in something that looks a little bit different? This is an 8. It thinks that this 8 is an 8. It also thinks that it could be a 6. But if we look over here, it looks like 8 is highly likely, but 6, which is the next likely one, is not very likely. It's very certain that we're looking at an 8 here. So what is this doing? How is this working? And like, how do we kind of get a feeling for what's going on here? So let's take a step back and sort of, I need to assume where you guys are in your math understanding. And I'm going to take a couple of guesses as to where you are, and feel free to, at any point in time, fill in your own knowledge so that you can sort of take what I'm saying, which is at a basic level, and try to fill in even deeper. And if you don't get what I'm saying, please throw a question in there, because I would love to be able to answer it for any level of mathematics. So what is happening between not this flattening layer, but these 2 layers? Well, essentially what we have is a level of math called linear algebra. So if you've taken college math and you've done linear algebra, that's what we're truly talking about. But let's go ahead and go into analogy land. So you guys might have had like gum in your mouth before, and you went to spit it out. And when you went to spit it out, you maybe like put it into your hand first, and you had this malleable surface. Maybe you've done this with taffy, maybe you've done this with gum, maybe an airhead. You get like this like malleable putty almost. Putty is probably the one that everybody's sort of played with as well. So once you get this putty, you sort of have the ability to take an object and rotate it, stretch it, pull it. It turns out you can rip it, but let's ignore ripping the thing. You can take it, you can stretch it, you can pull it, you can kind of take one side and put it next to another side. you can make the putty in a shape, in an orientation you wouldn't normally be able to do. Now, let's look at this object right up here where I drew the number 8. That's a piece of paper, right? So imagine you have literally a piece of paper, like a sheet of paper, right? And on this sheet of paper, you just wrote the number 8. What you're trying to do is you're trying to get this thing to basically interpret what is this paper object and how does this now turn into the number 8 in computers? Well, using a set of linear algebra and a whole bunch of, let's just go hand wavy magic stuff, it's actually math. There's a lot of fun math inside of it. What you're able to do is basically attribute the surfaces of where we just wrote the number 8 onto this piece of paper, right? So I could write 8 onto here, but unlike what I can't do on this paper, I can't pull and I can't stretch this paper. Well, what if I were to have put that instead onto that piece of taffy or on that piece of gum that we were just playing with? Okay, well, I write the number 8 on this piece of gum. First, let me spit it out. All right, so now I've got a piece of gum. Let's flatten it. All right, let's write our number 8 on our piece of gum. I don't have any gum, so sorry, I'm just pretending. And now you can take that 8 and you can stretch it, you can pull it, and you can make it into this weird looking kind of transformed object. And what do you want to be able to do with this transformed object? Well, at the end of the day, what our algorithm is looking for is which one of these 9 classes it looks most similar to. So quite literally, what is the magic? What is the math that's being done between these? It is the machine learning figuring out how to pull and stretch that gum, or if we were to go into the terminology of taffy, it's how to create the machinery that pulls and stretches the taffy again and again and again, which then takes it and brings it into a space where you're able to then ascertain, oh, well, these being lit up like this mean this, and these being lit up like this actually means the number 8. So how I wrote the number 8 there, what if I wrote the number 8 like this? What does it think? Well, it thinks it's something totally weird because, first of all, that is not an 8. I mean, it's an infinity more than anything, but it doesn't actually know. But look at this. It actually thinks that it does sort of look like an 8. It's got some percentage thinking, well, I mean, I don't know what the heck I'm looking at, but that certainly looks like it could be an 8 if you're like sideways. Like, I don't know. So it's very interesting what this thing has. And what's really even more powerful is it says that its second guess is that this is an 8. How many transformations is this thing doing? So right now, this is taking our basic space. This is doing 27 by 27, our input picture. So this is literally a times 1. So this is a 27 by 27 picture times 1, which is 1 dimension of color. So we have a grayscale picture coming in. And what this is doing is 2 layers of fully connected into basically, or you could also call it 2 hidden layers. Or actually, this is technically one hidden layer. So this is taking this object, it's doing 1 layer that we don't know the exact specifications for. So this is 1 hidden layer. And then here's our output. So this is doing 1 true transformation, but it's doing 2 transforms onto the data to go from our correct data to this format, and then from this format into here. So it depends on exactly what you mean by that. But conceptually, essentially, this is 1 or 2 transforms. You can also technically view it as 3 transforms because one time you have to flatten it, but that's a constant transform. And that's actually only true in the fully connected network type. We'll talk about some of the other ones. Actually, we can do that right now. So what happened here is you might have noticed we got this 8, and this 8 was all weird looking and sideways. It did guess that it could be a 2, but I mean, it also said that this could be the number 8. So let's go over here to a slightly more complex looking network, right? So this network over here, it came in, we had the single number on the bottom. That's what this is down here at the very bottom. It also then had 1 layer, which is flat, another layer, which is flat, and then a final layer, which is flat. We actually have that exact same thing up here, right? So we have 1 layer, which is flat, a second layer, which is flat, and then a third one. So we have the same things. It turns out there's all of this other stuff happening first. Okay, well, let's just, without paying too much attention to that, let's just go ahead and write that in and see what it guesses. Okay, well, this network completely guessed something different. And it actually didn't get what we had potentially wanted in there. So this is to show you that if somebody gives you some data that you're not expecting, you can't expect machine learning to work perfectly. I'm actually doing my best to drive home a really important message that most people don't get when they're learning machine learning at the beginning, which is machine learning isn't a magic bullet. You're not going to like suddenly be able to do everything with it. There are a lot of edge cases that you can easily discover, which will basically mess up your system. Now, what is this edge case that we're looking at right here? Say you have a camera, and that camera is literally looking at the paper that we have right here. So say I wrote the number 8 on the paper. Let's see. Okay, yeah, no, there's no way you can see that. Do I have like a Sharpie over here? No, here, I'll just like sketch it in. So say we have the number 8 sketched very beautifully. And all of a sudden, this is being read from like a webcam. What if the webcam was sideways because it's on a robot and that robot is moving around the space? This is an 8. This is an 8 no matter what orientation this is in. Why would it suddenly, once it gets up to this or actually technically it's closer to this orientation. Once it gets to this orientation, why would it suddenly not see it as an 8? Well, that's actually a huge like question and problem inside of machine learning. And a lot of people, when they're first learning it, don't realize that that's something that you might need to look out for. So every time I teach this class, I try my best to make sure that everybody sees that this isn't a magic bullet. But that said, let's see how much magic we can actually do with this. What it turns out is happening here is this is right here, a very small network. This right here could actually be built to about 10 times as large and be still real time. And in that solution, it would easily be able to capture if this was sideways or not. Why do I say 10 times? That turns out to be the number of rotations you would need for your object, plus a couple of repetitive ones. We can go into that if you guys are interested offline. That's something that if you're looking into machine learning a little deeper, we can actually talk about. So let's stop doing things sideways because those are clearly not 100% working. However, look at this right here. I wrote 8 sideways again, and it got it on its first guess. So it's not that it doesn't do it. It's just that it's not optimized to work for that. Okay, so cool. That's all well and good. Let's go ahead and try and see a little bit deeper into this and get a little bit more understanding as to what this is doing. Let's pull this taffy. Let's really like stretch it and pull it and understand. So previously, we were stretching and pulling the taffy, and we only had a single way to stretch and pull it. The way we were doing it was a concept in linear algebra, which basically says I can pull and I can stretch, but while pulling and stretching, I can't rip it, but I can put things next to each other that weren't next to each other before. This is very important. So I have some like blue tack over here for like putting up posters and stuff like that. So what you're allowed to do is you're allowed to pull it. You can stretch it as much as you want, but once you rip it apart, that's no longer allowed. You can have things as far apart as you want, just you're not allowed to rip it. Now, that is not 100% true, but this is conceptually what I want you guys to pick up, because what actually is happening in machine learning is it does truly let you rip the thing. It is nonlinear. It doesn't force you to have linearities. It's just if you can conceptually pick up that there is a forced linearity in there, it lets you think about some of these next things a little bit more simply. Okay, so let's go into this next step. What do we have here? This is what's known as a fully connected network. We could actually talk about what's going on each layer. And actually, you know what? Let's do that before I go to the next image over here. Let's go to what's going on in each one of these layers. So how is it that each one of these different colors gets associated to each one of these different points? In this first location, the way this happens is literally what it's doing is it's looking at where this is unflattened onto this object, and it's saying on the picture right here, this pixel, where is it land onto this 27 by 27? If it's like, if that color is shaded in, so if I like shade it in, then more of them will be colored on. So if I like really go in and shade the whole thing, you'll see that like a whole lot of this is now becoming like light blue. Whereas like with nothing shaded in, it's completely dark. So if I then go like that, we got like a whole bunch of parts that are shaded in again. Okay, so what we have here, oh, whoops, apparently I'm still drawing. Didn't even know I could do that. What we have here basically is a network which is taking our data, and you can see the colorization as it's moving through. But what is this colorization? What do these things mean? Well, if we go over here to a really cool project, and I'll go ahead and drop this for you guys as well, what you're able to do is you're able to actually see what's going on inside of this network. Okay, so what is this and what is this project? What am I looking at right now? What am I showing you guys? So this is something called covenet.js. This is actually a very, very old project. There's now tensorflow.js, which is the superset of this project. But tensorflow.js doesn't have quite as beautiful of a visualization as these guys do, or as this guy does, karpathy. This is actually just a single person's project from Stanford. But yeah, so what this guy did was he built a project which basically lets us visualize what's going on inside of this, oops, not this one, inside of this two-dimensional space. So let's go ahead and, I don't know why I keep doing the number 8. Let's do like a 6. There we go. So if we do like a 6 in here, we can actually take a look at what's going on. So first things first, what is this that we're looking at? We have our input. We have 720, whatever that was, 29 of these, this object. We have one hidden layer, and then we have our output. So if we go over to here, we have our input, which is a picture. And this one is going to give us 2 hidden layers. And this one will then give us our output. So it turns out that our output in this case is 2 different classes. And we can look at the difference over here if I pull this over to the other side so that they're not so far away. This one has 10 different cases that it can output to. What we're looking at here has 2 different cases. What are those different cases? One is green, one is red. That's it. We have different cases. We're going to be using this activation function, tanh. Don't worry too much about that. This is important, but it's not important at the moment. And what is important is this tells us that this is fully connected. So we're talking about this setup right here. And inside of this setup, basically what we have is we take our data and we're going to transform it. We're going to transform it again, and then we're going to get our output. Cool. So what does that look like? So let's take a look at some data. Here's some data. And some data in this case is, what if we have a bunch of points in our XY grid? And in this XY grid, they all kind of cluster around the center. Those are our green ones. And they're farther away from the center. Those are our orange or our red ones. How do we view this space? Okay, so one way to view this space is by looking at the fully connected layer. So this is the layer of the information that's coming in directly. You'll notice that this is literally the same picture that we are looking at on this side. This is, I mean, there's nothing different here. We can flip the axes. I mean, that's kind of interesting, but that's not really useful for anything. So cool. Let's go ahead and get to the first axis so that it's not in a weird orientation. So then what we can do, so what we just did is we just looked at what the input data looks like. Then what we can do is we can look at what the orientations that exist inside of our first fully connected layer look like. So if we go into here, we can actually see this data right here. Once you pass it through a function called tanh. Now, I'm not sure if you guys know what tanh is, but this is a function which is relatively well known for machine learning to be a squeeze function, or if you have a TI-83 or any of those style calculators, this is like that hyperbolic S function that shows up on the back of your calculator. It's actually, technically that one has different A value, so it's a little bit sharper, but whatever, it's the same thing. So what we have here is this function actually right here. This is the way you can write it. And this is the hyperbolic tangent function. And what this basically does, and don't worry, you don't need to know what this is exactly. I'm not being like, yo, you guys need to know all this math. Like, no. This is all done for you. What this does is basically, this says basically, we'll take some input and we'll squish it between 0 and 1. Actually, -1 and +1 in this case. Cool. All right. So we have this really cool project over here. I'm looking at the wrong spot because I moved it over here. What this is basically going to do is it's going to take our data and it's going to run it through, like, don't worry what this function is exactly. If you'd like to know what that is doing, go ahead and run that through a calculator. This is taking some function, which takes your input, and it's doing e to your input minus e to your input plus e to your input minus e to the negative input. Like, sure, like that's meaningful to me, 100%, totally. No, that means nothing to me. That just means give me a number between -1 and +1. And we'll train the values that go into here. That's literally what this is saying. Okay, so what this then is looking at right here is this is saying we've taken our data and we're going to put it through our first transformation. What this is actually doing is this actually has 6 separate neurons, and we're only looking at 2 of them right now. We're looking at the first and the second one. So what we can actually do is we can look at our data transformed through all of these different dimensions. Actually, very cool stuff. I know that this is a little bit over the top and over like maybe the original version of what you guys might understand immediately, like what you could see from here's head, but I think this is very cool for you as you moving forward to see this. There's also another one, playground, that I want to show you guys. Play, oh my goodness, if I could type. TensorFlow. And this one is literally showing us the exact same thing as what we just saw a second ago, right? So here's our same exact data. Except for now what you can do, and here, I'll go ahead and drop this so that you guys can use this. And I highly, highly suggest you play around with this project. What you can do with this is basically up at the very top. And if you miss anything of what I say inside of here, don't worry about it. I'm not going to say everything. A lot of it is right down here. And even more of it is inside of the like how-tos. There's like click in and get how to, let them know, do certain things. Like there's all of these different things that you can do inside of here to get more information. But this is a really great little subset. Basically what this project does is if we take a look back over here, we actually already have a solution to a machine learning model, which will do exactly what it is that we're looking for over here. So what this is trying to do is this is trying to separate the middle data from the outer data. And we're giving it different features that we can separate this thing by. In different neurons, and then different outputs. So we already know that we have two different classes. And what we'd like to do is basically just something simple to be able to basically pull out what the different interactions are. It turns out the answer that I just threw on there is mostly perfect for like a lot of these different ones. But it's not actually that important. And what you'll notice when I say mostly perfect, I mean, this is an approximation, right? So we have all of this orange space, which clearly is correct. We have all this blue space, which is clearly correct. But what is this blue space down here? Why is it there? What is it doing? Like that literally is not supposed to be there. That's incorrect. But if we go over here to one of these other functions, it turns out that the setup that I just showed you right here, it does a really good job on most of them. But here's something funny. It actually fails miserably on this one. And this is actually a challenge set that I would like most of you guys to give a shot because it's very fun. So this is data that is completely false. Like you would never actually see data that looks like this. It is specifically crafted to be difficult for machine learning. What the goal is basically is to get a spiral group and then a second spiral group. And with those two spiral groups, you'd be able to separate out your data. This is something that in general is actually incredibly difficult to do. There is a solution to this that is known as the kernel trick, which would go through and fix a lot of these things. The kernel trick is implemented actually inside of Sine X2. But it turns out that this is actually a very difficult to solve question. And what's happening inside of here is a really interesting visualization of the corner cases that you guys as like entry programmers inside of this machine learning space might interact with. And what is this type of problem, like sort of like, what is it? Well, this sort of a problem is basically the type that would say, hey, I have some data that I am not good at cleaning. How do I make it so that I can use machine learning to like fix it and do it for me? Well, yeah, look, I mean, you can do that. Like this is basically saying you could give it any horrible data, even if it's completely like purposefully made as bad as possible. And you can use machine learning to solve it. But like, I don't know about you, but I see a bunch of areas like right here that look wrong. This looks wrong. This area right here, I would assume belongs to the blue just because it like continues along on that path. There's all these different things that like the machine learning doesn't assume properly. So what we'd like to do with this is basically see if we can do a better job. Well, let's take a next step. So everything we've been talking about right now is inside of here. We can actually take a look at what this whole area is right over here. So let's take a quick aside. And before we go into convolutional networks, I'd like to actually take a backward step into something that is used in the past more than right now. But this right here, what we're looking at, this is the solution to what I was just alluding to, where we have all of these different issues where these different sections, they get kind of like completely kind of gunked up. It's hard for you to figure out where they belong. It doesn't work all that well. And also on this, wait, was it this data set? Yeah, on this data set, where we get random extra pieces, we can also figure out how to clean this up as well. It turns out by adding the kernel trick on this one, it works really well, but let's not worry too much about that immediately. Okay, cool. So let's go backwards. First things first. In order to go backwards, we need to describe a little bit of how the history of machine learning worked. So today, nowadays, we have really strong computers. And again, anybody who has any questions, feel free to stop me or just throw them into the Zoom chat. I'd be more than happy just to go over anything. Okay, so nowadays, we have very strong computers. These strong computers can take our input data and it can convert it into such a way that we can actually run it through these machine learning models. I believe it was 1970s. It could have been the 60s. The perceptron was first conceptualized. I believe it was a Russian computer scientist, but I'm not 100% positive. It's been about a couple of years since I was in college. I was going to say exactly how long, but it's been a couple of years. Essentially what happened was this computer scientist came up with a concept which basically said, given some input, I should be able to like put a mathematical formula, and they were back in like the 70s, very close to guessing that this formula was going to look like linear algebra, but they would put in a formula that would then basically pull this thing apart and be able to do some sort of learning as to how to change the formula over time. So there was this basic idea of what backpropagation became today, where basically these guys were able to come up with how it would work, but they did not have the computational power to be able to prove it. They, until really the last like 10 years or so, it's been almost computationally infeasible to do any of what I've just talked about. So how the heck has all this existed up until now? Well, it turns out a lot of this can actually be done by a lot simpler of methods. So let's talk about one of those methods. And it's actually one of the ones that I think is one of the more important ones because it's actually still used today. Technically, it's a variant of it that's used today, but it's the same idea. Like all you really need to do is get an intuition of it and you can use the variant. It's not that big a deal. And in the intuition, if you've gone to high school, you probably actually know what this is already. All right, so let's talk about a concept called k nearest neighbor. So k nearest neighbor is actually, do I have a visualization of it? Probably not. K nearest, KNN. Oh, 3 n's, sure, why not? Just 2. It's actually just 2 n's. And here we go. What we want to do is basically, I wanted to show you a quick picture of this. Okay, great. That's actually a perfect picture. Okay, so k nearest neighbor. What is this and why did I say that you guys probably have experienced something like this in high school? Okay, so, oh, sorry, my wrist is suddenly needing to be cracked. Okay, cool. So if we take a quick jaunt all the way back over to here, we randomly, it felt like all of a sudden, went from taking a picture from here to suddenly saying, cool, we have some XY data. What? How did that happen? Well, what turns out to be the case is in older versions of machine learning, what you would do is you would do something called vectorization. And this is still true today. You still do need to do some level of vectorization. It turns out a lot of the vectorization is give it all the data and let it do it automatically, but you need to do some level of vectorization. And with that level of vectorization, you can basically figure out where the object would exist on a 2-dimensional space. So this type of a formula that takes an X and a Y, that's totally fine. This type of a, this type of a formula which goes from a XY into something else, that's actually also the same thing. So what is this concept of vectorization? Well, let me give you an example. And this example is directly used for KNN. So say you are a like freshman in high school or junior high school or like college, whatever, it doesn't matter. I'm just assuming that you've all gone through at least freshman year of high school, so that's why I use that one. So say you're a freshman in high school and this is a new school, this is a new town, you've never been in this area before, and you'd like to figure out who your friend's going to be. You know that you like computers because you're at this place. I'm just going to assume you all like computers. I don't know. I feel like it's a safe assumption. You also know, and this is now no longer a safe assumption, that probably some percentage of you like video games. You also know that some percentage of you really like horror movies. Others of you really like romance movies. Others of you really like to watch like Rick and Morty. Some of you don't like to watch Rick and Morty. We have all these different pieces of information that we can pull out about each one of you. Well, what if we were to just take 2 of those? If you just take 2 of those, what if we were to say the grade that you're in, and this is 0 to 16th grade. So we're going to allow 4 years of college, and anything after your 4th year of college is 16, just so we can like simplify that. And we're going to have the other dimension be the height or the number of years that you've done programming for. So what we could then do is we could say, given that you're this age and you've been programming for this long, here are the people who are most similar to you. Is that a good assumption? Absolutely not. That's just 2 dimensions. Why would you assume that a 2-dimensional space could give you a good approximation of us humans who are hugely highly dimensional? Well, K nearest neighbor is trying to answer that exact question. They use the vectorization concept to take our samples. So right now we're looking at a 2-dimensional view of a high-dimensional space. You can do this anytime. You can take any high-dimensional space and just take a 2-dimensional window of it. You just imagine having like a 3D object next to you, and then having another 3D object like your camera or your phone in this case, and taking a picture of it. Now on my phone, I have a 2-dimensional representation of that 3D object. If you really want the more complex version of this, you're in calculus and you're taking the projection, but that's not that important. We don't need to think that deep into it. TLDR, or summary, sorry, I'm a little Reddit right now. Summary is you take a couple of these sample points, a couple of these ways to think about the people, and you basically start creating a cohort or a clique. So K in this case actually stands for the number of, the KNN, nearest neighbor. Yeah. So K stands for your count. K is your number of. Yeah. I had to do that like and then figure it out and go backwards. So K is your number of nearest neighbors. And in the case of what we're looking at right here on the screen, we are doing KNN 3. So in KNN 3, basically what happens is you take your sample point. In this case, it's the purple or the green one rather, and we're putting it onto this 2-dimensional space. And we'd like to say, what 3 points that are closest to us, what is their class? So let's go back all the way to us for our first day in like freshman year of high school. You're going in, you're walking into the school, you see a whole bunch of people hanging out over in the like drama area, and you see a whole bunch of people hanging out over in the computer science area, and you see a whole bunch of like people hanging out over in the sports area. And we already figured out that we're a bunch of people who like computers. So where would you go? Probably to the group that's most similar to you. You would go to the people who have the most similarities, therefore basically making this one a red sample. So this is basically the idea behind all this, where it's just saying, I have a new sample, let me put it on our graph and see which other samples are closest to it or most similar to it. So this is wonderful. This actually turns out to be an unbelievably powerful machine learning technique, and it's actually still used today a whole lot. It's not used as like the front of the things, but I use this actually in the type of machine learning that I do for art stuff. And I have a whole bunch of friends who actually use this for their robotics style competitions. And I also have a lot of knowledge as to just generally how to take our old versions of what we're going to talk about and convert them into here. So I'd like to just make sure that you guys understand that basically what I just went over for the last couple of minutes here, it's not useless information. It's just this is old information that is now going to be pulled into the new stack. So what does that mean? Let's take a look now all the way back over to here, where we are now taking one step beyond what this version was. So this is a fully connected network. So just for starting all the way over, this is what existed in history. This is a no network, just all of our sample points exist in like a .csv with an X and a Y, and if they're blue or if they're red, it's actually usually database, but that doesn't matter. We then go to the next level of this one, where they're saying, well, you can take all of those data elements and you can put them into a model, which can learn what the approximation of that space looks like. So when you see a new one, instead of it needing to see how close it is to that other one, you can just see how close it is to this weird new like sample. And that's actually really powerful because this new sample is what, like 100 elements long. And it's a lot easier to see if something's closer to something else in 100-dimensional space than in 2-dimensional space, because there's more like pockets. And what do I mean by that? If you have a piece of paper and you're trying to say how close are two objects, there's only a circle, a flat circle of space that they can be close to each other in. Now, if I have a cylinder and I want to see how close things are to each other, there's actually now a sphere of objects of what is closest to it. So the higher the dimension you're in, the more similarity or closenesses that exist around you. This is just generally true and important for you guys to sort of pick up inside of the basic understanding of machine learning. And again, I know I'm just sort of throwing a bunch of terms out there and sort of hand wavy about a lot of this, but I hope at least some of this sort of makes some sense. Now let's see if I can find this. Learn with me machine learning. Google. I think it's called Learn with Me. Oh, that's not what the name of this one is. Teachable machine, maybe? Teachable machine. That's what this one's called. Okay, so I'm going to give you guys a project, which is based off of this one right over here. And this project is amazing, but we're going to talk about this one for a little bit here. What this one does right here, oh, what, they use the webcam now? Oh, dude, that's amazing. Okay, what this one does is takes what we're about to talk about and gives you a web browser version of it, and then I will give you some standalone code so you can run it on your own and not need to worry about it running inside of their system. And you can run it on the web browser. You can do it on basically anything. Okay, so let's go over to here and let's take our next step. So first things first, what was the step that we had just before this? We had the number 6. It was put into here. It was flattened. We did some math to it. That math was for some reason done on taffy. Who knows? Maybe the person who did it was hungry. And then it was done on taffy again, and we got our number out. Wonderful. That's cool. We then took an aside to talk about what happened in the past, which is great, but that's not what we're doing anymore. What's interesting is to look at what was happening right now. So let's take a look at what's happening right now. So let's go ahead and write our number 6, and let's take a look at this crazy looking graph. So first things first, we'll notice that it gets the answer correct. Wonderful. What is this thing doing? This is doing something called convolutions. Yeah, so it looks like we're through our design phase and now getting into the functionality. Exactly. We are now getting past the basics of what the concepts of design are. And I will show you a project that will let you go all the way from designing all the way up into utilization. That's exactly kind of what we're looking at here. This is one more step of design, but this is more so just so you understand what is into the design nowadays. And a lot of what's happening in what I'm describing right here, you actually don't need to directly interact with yourself, because a lot of the time, unless you're building the machine learning model, you're just using this output up here. And we'll talk about that in a second. That's actually why I talked about KNNs a second ago. Okay, so what's going on here is we have this bottom portion. This bottom portion right here is exactly the same as this bottom one right here. There's nothing different about that. The one part that is different is immediately after this bottom portion, we have these 6 layers or objects. Well, these 6 right here, they look like weird versions. That's about all I can say. They look like weird versions of the one below it. And if you imagine taking a picture of something and then getting the negative of that picture, that's kind of what you have for some of these. That's not 100% true, because quite literally, they are random. The way that they're created, it's using basically a 26 or 27 by 27 dimensional space. It's got a 3 by 3 filter. It's taking that filter and it's basically deciding how to read the space below it. Like these are not really interpretable filters, but what you can imagine is basically this is taking it and taking like a inverse, but each one of them are different types of inverses. So one of them might be the inverse of when you take a picture with the lights all like white. Maybe when you turn all the lights to red, you take the inverse of it. Maybe that's what this one is. Like I'm saying maybe because really we have no idea what these are. This next layer up is a sample of the layer right below it. So we have our first layer, we have the second layer. The second layer is sampling from the first layer. This third layer, it's not touching the first layer, it's only touching the second layer. So we have this second layer, which is now reading all of this data off of here. And it's basically saying where there is a average of the group coming down below. So you see those four like blue lines that are coming out of here that are moving all around. So those four blue lines, those are the same as this convolution, C-O-N-V-O. Oh my gosh, spelling is hard. Convolution example, get. I believe this is the one. Yep, this is the one. So we have this beautiful new concept that we're not going to talk exactly about what a convolution is, mostly because it's not that important. It turns out knowing what the operation is doesn't give you that much help. What it does do, though, is it gives you a little bit of a mental leg up if you do understand it. But like if you haven't taken linear algebra, don't worry about what a convolution is. And I'm not even talking about linear algebra level 1. I'm talking about level 2 or level 3 of linear algebra, because like this is actually a relatively complex concept where, in my understanding for analogies, basically it's taking a space, approximating a different space. So if you have like an object in front of your face, right? Like that's right in front of me. If I squint my eyes and cover the other one, or like squint both eyes and cover one a little bit, if I draw what's in front of me, that would be an approximation of what the convolution is doing. That's like a really, really like bad analogy, but I want to kind of drive home that the convolution is an approximation. Now, it's not always an approximation that down selects. It could be that I just put glasses on. So this is the case where I'm squinting, right? So I have a smaller space that I'm looking at, that I get out of looking at a big space. So the blue is your input, the green is your output. So I'm squinting, so I can only kind of see a little bit. So that gives me like a bad image. Whereas I just put on some really good glasses. So now I can see one-to-one, a beautiful, perfect image. You have all these different ways of kind of conceptually seeing the picture below you and taking that data and pulling it and combining it together. Convolutional networks, essentially what they're doing is just more linear algebra. So we've got that going on, and that goes into here, which each one of these basically is just reading the samples of the object below it. We then get to this layer, which is basically doing the exact same thing as the one below it, except for now it's looking across multiple of them. And this is just doing the same thing as this layer right here, where it's just making it a smaller amount of them. And then you'll notice that these three layers right here, that these look the exact same as the three that we have right here. And the reason, oh, eyelash, super big eyelash. All right, the reason these look the exact same is because they actually literally are the exact same. It turns out the thing that's different about them is there isn't 729 of these right here, but that's just because this has been downsampled by all of these. All of this right here, if we were to downsample all of this so that we're no longer just looking at that 6 and instead looking at a bunch of smaller versions of the 6, well, cool, that could be happening. And earlier I said, we don't really know what these filters are doing. We can imagine it like taking the negative. Look at these filters right here. Like, I mean, if you understand what this is doing, like, please tell me what this means. But like, I could not for the life of me understand what this means, right? Like, because this is saying colors. It's pretty, don't get me wrong. I think it's very pretty, but it looks like a heat map. And it's basically a meaningless heat map. And I want you guys to sort of have that understood, because like, you're not going to look at all this data and be like, oh, look, that's like Neo, like flying, like we got it. We know that he's flying right now. Like we don't have that level of the matrix going on right now. We are very much so like, okay, look, we've got like this calculation going on. Oh, look, it's the number 6. So like, you know, all those articles where they're like, yeah, we're going to have like machine learning and it's going to take over your job by like next Thursday. Good luck. Have fun. Yeah, no, you guys have forever. Don't worry about it. Like maybe it's going to be like 3 Thursdays from now. Like you got enough time. That joke brought to you by not enough time coming up with the final answer to what I'm trying to say. All right, so what do we have here and what's going on with the ending portion of this and why do they look so similar? And also, why is it that I brought up KNN? Well, what we have here is basically a really interesting paradigm. We have something that can take arbitrary input, right? Like I can draw whatever I want over here. It will then put it through this network. And after putting it through this network, it will guess what its output is. But say we don't care what this number is. Say I want to use this drawing thing to do something else. Like I want to do some machine learning and I want to just use this tool without thinking in the slightest, how do I train this or how do I do anything? Well, it turns out using transfer learning, which is super, super important, we can do exactly that. And that takes us over here to teachable machines. So let me drop this link for you guys. I highly suggest you guys play with this one too. I think that you should play with this one after playing with the TensorFlow Playground, just because TensorFlow Playground, English. Anyway, TensorFlow Playground gives you a lot more like malleability and understanding of the space, whereas Teachable Machine, it basically is the entire, like it's everything. It does literally everything you might want. Okay, so first things first, let's see if this can take my webcam. I actually don't know. Oh, okay, well, you guys can look at my desk. That's fine too. Here, I'll just move that webcam off of my desk and put this at my face. This is a really bad webcam, so I'll have to hold it. Okay, cool. So, hi. This is weird. I wonder if I can push it. Oh, apparently I got my Google device to talk to me. Okay, so can I get this thing to be my other camera? Because that would be a lot easier. The answer is no, so screw it. That's not a big deal. Okay, so basically what we want to do is we want to have a sample like this, and we'll just take a couple samples like that, and then we'll take another one right here, and then we'll take a sample with me looking at it, and then basically what we're going to do is we're going to click this button right here, and this is going to take it a second, right? So this is basically going through and it's taking the pictures, 21 samples of my face sideways and 33 pictures of my face looking at the camera. It is preparing the information and it has now gotten a sample. It now thinks that it has done a decent job. Don't switch tabs. You must leave this tab open to remain training. Ooh, I've never seen that before. That's cool. Okay, so it's going to take it a couple of seconds because these pictures are some size. I actually don't know what size they are off the top of my head. But what's interesting here is if I close this right here, we now have the side of my face. And if I look at you guys, if you look right here, we have it switching between class 1 and class 2. Look at all that programming I had to do just so that we can use my webcam so that you guys can now tell between class 1 and class 2. Also, hey, check it out. We got a whiteboard with a bunch of text. So cool. What happens if I do something different, like put my hand up here? Or accidentally knock over something on my desk because I pulled my webcam too hard. Essentially what happens is we all of a sudden have a different class that this thing hasn't seen before. And we don't really have any information for. All right, I'm gonna put that back up there because that actually kind of kills my arm. I'm gonna go ahead and close this. Yes, go ahead and leave, we don't need that. And what that is doing is basically taking everything that we've just seen so far and taking a next really big fun step. So what it's doing is it's basically saying, hey, I can take any arbitrary input image, right? So why not the picture from your webcam? So this is the picture from the webcam. I mean, it's not, clearly this is whatever I just drew here, but this would be the picture from the webcam. It's then taking it through this exact same type of system. It isn't the same system, but it's the same type of system. And then it's outputting at the end, instead of a number, it's saying, oh, well, we're going to cut the head off. Literally, we're just going to lob it off right here. And what we're going to do is we're going to use this right here as the input to a new system. What is that new system? Well, that new system is a KNN. Hey guys, why did we learn a KNN earlier? Because it turns out in today's machine learning, they use, for real-time systems, a lot of really old techniques on top of the new techniques. And then they just chop the head off the new technique and then apply the old technique because the old techniques are unbelievably powerful. Like these, like like unbelievably intelligent engineers spent a long time coming up with how these things would work. So why wouldn't we use them? So that's basically one of the big things I want you to take away from this. Anything that you guys learn in machine learning, it will probably not be what you use tomorrow, but it will likely be something that it's a concept that lets you chop the head off the new Hydra and create your own version. It's super important. When I was in college, when I was learning this stuff, KNN was actually one of the bigger deals. Instead of just an aside that they would throw at us in less than an hour-long conversation. No, that was like a week-long thing that we went over. We actually also went over k-means and all of the other variants of it. What I'm saying to you guys is there's no reason. Don't worry about it. It's just a bunch of clicks. How do those clicks work? It's exactly basically just taking your groups and figuring out which one looks more similar and closer to one another. And once you've done that, you have the ability to kind of group them up and have something fun. All right, so I told you guys that I was going to try to package this into an hour. So I'm going to go ahead and cut off the next statement and instead drop you over to a link. And if you guys have any questions, we can definitely go deeper onto anything. And I'd be more than happy just to sort of push forward. Also, this is the first time that I've given the talk in this orientation. Usually I focus on the early stuff like KNN first, and then I move forward. If you guys would like to give me any votes as to if you like the way that I gave this talk, feel free to shout that out. This is a huge topic. There's a whole lot more in here. So like we've barely scratched the surface. We're doing like a sprint. All right, Matisse, I can't spell my own name. Projects. Okay, cool. Let's go to GitHub. I don't know why I did it like this, because I am not thinking. That's probably why. Okay. What? Did I not go there? I guess I didn't. Whatever. Wait, isn't that what I typed? Okay, whatever. It's fine. I swear that's what I typed. Okay, so you guys are more than welcome to come on over to this project. And this project is exactly what we just saw over on Teachable Machines, but it's a little bit more powerful. And just so you guys have a little bit of intuition as to how much I'm like more than happy to let you guys mess around with my code. Thomas, this guy right here, was actually one of the previous people in a class that I taught. He pointed out that I actually forgot to write something so that this works over on AWS. So he's now a large contributor inside of this project. I mean, large as in he made a project change and nobody else has done it. So I highly suggest if you guys would like to be on here and have your name as somebody who I point out as an amazing person in the future, feel free to make pull requests. I'm more than happy to put you on here. This is just a test project. It's not like a big deal. For me to like have everybody's name on here. I'd be very happy to have you all on here. Okay, so what is this project? I'm not going to go too deep into the code because I like to sort of give us a quick version of it. But what is this thing? So this is basically the teachable machine, but a little bit more powerful. So first things first, we're allowed to have two separate main classes and then a third type of class. The two separate main classes, we can define how many of these inputs they have. And this actually is defined over inside of, you can do it here, but that's actually defined as a template that you can send to it. You can actually send inside of the framework how many different classes each one of these has. So this is nice. This is fun. You can also tell it how many different frameworks you want to be able to use. That's great. Not a big deal. Why is this important? Why is this thing interesting? Well, what this lets you do is this basically says, first of all, let's use Mobilenet v2 instead of v1. So that's already a tiny upgrade over the other thing. And what it's going to do, sorry, what is Mobilenet? Mobilenet is basically, we were looking at a specific network right here. I believe that this one is called the AlexNet. Let me see. I believe that that's what this one is called. Yeah, so this one is what's known as the AlexNet. And it's just a picture that then gets shrunk down a couple of times, put into a couple fully connected, and then flattened into our softmax. So that's what this is right here. We've got our object, and then it's convoluted a couple of times, and then put into a softmax, or a fully connected into our softmax. So this is basically this one type of machine learning model. And what they have inside of here is, wait, I think I might have just gone back a step. Wait a second. Did I just close the wrong one? Yeah, I think I might have just closed the wrong tab. All right, whatever. We're just going to go into this anyway. Okay, so anyway, sorry, I have way too many tabs open on way too many browser windows. I have like 6 of these windows. So what we got going on is basically the ability inside of here to just like launch exactly the same thing as what we had on the other side, the teachable machine. What's more fun about this, though, is you can actually use the inputs from this teachable machine to teach other portions of the teachable machine. So let me go ahead and launch this program. If I can remember where I put it, cd git. Okay, cool. And then Python basic. So when you run it and then you go to localhost, it will basically pull up your camera again. This is the exact same page as the other one. It's just, it's written by me, so it looks like crap. And I am serious. I just don't bother with writing stuff to look pretty. Hey, look, that one uses the proper webcam. I wonder why the other one didn't. Very weird. Okay, so what we got going on here is basically we can call this sitting. And then I'll just sort of capture a couple of these with me just sort of sitting here. And then this is just going to try to dynamically figure out what's going on. This one is going to be left hand. So I can put up, this looks like my right hand, I think, for you guys. I'm actually not positive. But this is like my left hand. So if I put my hand down, I'm just sitting. If I put my hand up, now it's got my left hand. If I go over to the other one and I just sort of have it with my mouth like kind of closed, and then another one with my mouth open. Now we can tell when my mouth is open or when my hand is up. Wait, that's not working 100%. There we go. Yeah, so now we can tell when I'm sitting here, when my hand is up, when my mouth is open, or when my mouth is closed. So these are our first 2 classes. And you'll notice in here something really interesting. We actually have less than 100 samples of data for each one of these different classes, and it's working really well. One of the things that I'd like to, and I see that it's 6 o'clock, feel free to let me know when we got to pause at any time here. One of the things that I'd like to kind of point out is machine learning normally needs like massive amounts of data. We're talking like hundreds, thousands of sample points. How is this working off of 13 and 25 different samples? Like, what do we do here? How did this work? And not only how did this work, but also how is it working so reliably for the sit versus hand, or the, let's see if we could do like a touching head. So hand, head, sitting. How is it doing so well? I don't know. Well, actually, I do know. What this is now doing is this is taking our input picture, our 27 by 27 times 3, because it's RGB. Oh, Doggo is making noises. Okay, cool. She just wants to be known. Doggo is right there. If you guys couldn't tell, that's a dog. Oh wait, right there. What this is able to do is it's able to take our 27 by 27 by 3 image and classify it into each one of these different, now 5 different categories. And with these 5 different categories, each one of them has less than 20 samples. So we have less than 100 samples. And with less than 100 samples, I'm able to tell 5 different classes apart. Well, this gets very powerful and very interesting very quickly. And I'm going to probably pause it at that and let you guys ask any questions if you have any, and otherwise kind of cut off. But basically what I'd like to say is everything that you've learned so far, everything that we have up until this point is inside of this project. So let's take a very fast look at it, just so I can kind of give you guys an overview as to what I mean by that. This is in the JavaScript, I think. Let's see. Yeah. Okay, so inside of the JavaScript, basically what we want to see here is we have this part right here, which is called Mobilenet, and we have this part right here, which is called our KNN classifier. Okay, so what was the very first thing that we learned about? We learned about one of these one of these fully connected networks. And then I said we actually nowadays use something that looks more like this. Well, this network right here is quite literally the same network that we have going on right over here. This is our Mobilenet. Mobilenet's more complex, but it's the exact same thing. And then the KNN classifier, that would just be this guy right here. That is also inside of here. So we've got 3 KNN classifiers and 1 machine learning model. And what this then does is it literally goes through and it adds into the classes the samples of your picture. So this is just at that class, add the data. What data are we going to add? We're going to get webcam. So we get this webcam data, we get this add example. This add example takes the information through a MobileNet, which is basically, it just takes your information and it passes it through a network, actually more like this one, passes it through a network. We lob the head off the network. We take this one right here, this whole string of colorful numbers, and we feed that into a KNN right here. And then we basically get our network that I'm now handing to you guys, which is this one over here, our final project. And the code for it is literally less than 300 lines. And a lot of this is comments and stuff you don't need. There was a question, let's see. The probability shows 1, it's rounded to 100. No. Okay. Yes and no. The probabilities are based off of the number of classes that exist inside of it. So is it rounded? Yes, but is it rounded? Like, are there other numbers that it can be? You'll see that like 0.6 is a high possibility as well. So basically what this is doing is it's taking the number of classes that it has. So let's see, what was this one? This was touch face. So this is taking the number of different classes that it has, and it's saying, given those different classes, let's see how probable we think it is that one. So in this one, giving us 0.6 a bunch of times, this is literally just saying between the two of these, there is a inconsistency of how much you've given the first class versus the second class. So 0.6 is where that middle exists. It's not exactly a good way to put that, but it's not basically rounding. It's a little bit different. Let's see if I can pull up the code so I can show you what this is doing. Oh, I did not have the code open. Okay, well, let's just go back over to here. And basically what this is saying for outputting to that place, where did I put my update function? Update class console. Here we go. So not this one down here. Update count. No, I was right the first time. This is just updating the thing. Right, so this updates the part. And what this is basically saying is, given the activation, so given the percentage of correct that this thing is, let's go ahead and figure out what its input into here is. So it's saying get what the object is and go ahead and give it this class name. We'll sell it what our percentage confidence is. So does it happen to be rounded to 1? Kind of, but that's only because of the way that the data I put in exists. It doesn't necessarily need to be that way. Now, another thing though, to completely answer your question, when we looked at, if I can find it, ReLU or tanh, which technically we use ReLU, not tanh, but when we used tanh, this forces our numbers to be between -1 and +1. So you can already rescale to be between 0 and 100%. You already know exactly what your bounds are. Hopefully that answers your question. If not, let me know. Yeah, I think that sort of is the major overarching concepts. I think that another kind of nice thing to know inside of here is a lot of the time, you guys don't actually need to build a lot of these models yourself. Like a lot of these things, they exist over at like, I think it's hub.tensorflow. Let's just go to hub.tensorflow because I can't remember. Oh, it's tensorflow/hub. Okay, they might have changed it. No, you're completely correct. It is basically the probability of the output of the model. It's just, it's not exactly between, it's a good way to view it. How you had there is correct. I didn't mean to confuse what you said. That is a good way to view it. It's just, it turns out there's more to it than that, just because of the way that we've done it. But in general, the way that you said is completely correct. So don't think that what you have there is incorrect. It's actually quite good. Okay, so Tfhub Dev. This is something that is super, super important to know about if you guys want to actually use machine learning in industry. This is a website that you will find yourself on every so often. Basically, what this does is it is TensorFlow's like host for a bunch of well-known models that you can basically just go through and use and not need to worry about creating the stuff yourself. So what does that mean? Inside of this project right here, we used a project called Mobilenet, and then we used another one called K-nearest neighbor. Where did these come from and how did I know to use them? Right here. That's the answer, actually, literally. I wanted to do a image classification thing. So I went over to the Tfhub Devs. Let's go ahead and clear all that. And then I clicked, I wanted to do a image processing. So you click over here on classification domain image. This will take you to all the different image classification models. And inside of here, now you can choose whatever you'd like. I happen to choose one of them. I believe this was like 4 years ago when I first wrote this thing. And the main model that existed that could run live was called Mobilenet. Now there's like 6 different versions of Mobilenet. I've never even heard of SSD Mobilenet. Like that's got to be something cooler and newer. It just came out today or yesterday, so that's got to be interesting. Yeah, I don't know. This looks the exact same, honestly, but it's interesting because there's all these different models that you might want to be able to use. And Tfhub Dev, this will host a lot of them for you. And what do you do to be able to use these things? It completely, oops, that's C#. We don't want that. It completely depends upon what language you're dealing with. If you're dealing with JavaScript, which ironically, I actually do my best never to deal with, but that's okay. If you're dealing with JavaScript, if we go over to here, if we go into our index.html, you'll notice that this right here is quite literally saying, go into our TensorFlow NPM packages and pull out the Mobilenet and the KNN classifier. And those are quite literally the string that is pulled from right here. Copy URL, if we copy this URL and we paste it right back to itself, we'll notice that this string right here, it happens to be like some weird whatever this like string is. That's just because we're pointing to that specific one. The other ones that exist like are here. And you can find them inside of the NPM package. And this NPM package is just on the CDN instead of pulling it from them directly. So it's like literally we can do this and get their machine learning packages. So a lot of what I talked to you guys about how to interpret the KNN, you don't need to understand how it works like verbatim. You just need to be able to call this. And now all of a sudden you have access to the KNN. Fun stuff. All right, let's see. Are there any other last second things that I'd like to make sure you guys see? Okay, I'm going to show you something that's in a completely different direction, but it's very fun stuff that you can do with this. So here's something that is, once you've gotten to a point of understanding, that you can just do some crazy stuff. So there's this project called Gaugan, G-A-U-G-A-N, and it's a lot of fun. You can do a lot with this project. So let's give you an example of what that means. So an example of that is, let's say we have like a building, and this building will be a house, and we want to just sort of draw it maybe like right here. And then we'll put it like that. Then maybe it'll have like a roof on it. Oops, that's not what I meant to do. Let's put like a roof on it. Okay, and then we'll just kind of fill that part in right there. Okay, let's put some landscaping. Let's put a hill. Let's put that over here in the background. And then let's kind of like have it go up like this. And then down through the thing. Let's just sort of fill that in and then fill that in. And then let's go ahead and do like snow, because that makes sense to me right now, all down there. And then let's do clouds all up here. Okay, cool. So let's see what that looks like. Right, we got to hit this checkbox down here. Let's see what that looks like. And now with doing zero drawing, like mind you, I drew this piece of crap over here, but with doing zero effort, we now get this thing over here, which looks interesting. Why do I say it looks interesting? Because let's roll its statistics. And now all of a sudden we can change what the drawing looks like and like where it is inside of the seasons and how the image is getting interpreted, all from the exact same input data. How in the hell is this happening? What are we doing? what is this? Like literally, what is this? This is craziness, isn't it? Like when I first saw this, I was just like, I was taken aback. I was like, this doesn't make any sense. How can you do this? Why can you do this? Really is one of the first questions I asked, actually. And the answer for both how and why is exactly what we just went over, right? We've actually talked about everything that's needed for this. And let's do a really fast like deep dive as to what that is. First things first, you need an input. This input right here, where you can draw and do whatever the heck you want, this is the exact same thing as this input over here. It's just over on this input, we've got more colors. It's not black and white. We can change the color, and the color means a different thing. So by meaning a different thing, all of a sudden we have different pieces of data that we can sort of put into and pull out of this overall spot. So why is that interesting? Why is that kind of fun? Now, all of a sudden, as like an art person, I can just sort of come in here and I can just kind of paint, well, badly, but I can just kind of paint. And by doing some random painting on this side, I can literally change what this is coming into the system. And because what they're doing is they're reading all of these variables, not caring about what's down here. They're reading all of these variables and then going up to this layer. They're actually doing it after doing a huge number of convolutions. So they're getting up to like this layer up here. Sorry, I didn't mean to rotate my screen. They're getting up to like this layer right up here. And then what they're doing is they're saying, actually, we don't need to just do that. We're going to take these and we're going to assign them to each one of these different classes, hand up, hand down, open mouth, closed mouth. We're going to like touching face, not touching face. We're going to assign those to different classes. And those different classes that you see, we'll let you draw them onto the screen. And by putting those different classes on the screen, we'll now have the machine learning model learn how to draw something from it. Like literally, you guys have everything to understand how a GAN works. We just haven't talked about why a GAN works. And if you'd like to know more about that, I'll give you like the super, super fast version, which is imagine you have a art thief and you have a curator of a museum. The curator of a museum wants to make sure not to purchase false art. By making sure not to purchase false art, they need to be well-versed in what false art looks like. And the more well-versed they are, the harder it is for somebody to forge the art. The forger just needs to get a little bit better than the person who's trying to make sure that it's not a forgery. Once they've done that, they can sell their false art. So they have high chance or high drive to want to be able to learn. And the other person has high drive to want them to not be able to do it. So you have opposites. One's trying to optimize down, stopping it from happening. The other one's trying to optimize up, happening more often. And essentially, they're fighting over the same high dimensional surface, a human being able to tell if this exists or not. And we then, as a result, can change what the inputs of how it's doing this transformation are happening. Now, I did a whirlwind there that was all over the place, and especially that last example, I really wish I could go deeper into how and why all these things work. But I really feel like if we wanted to, this was going to take a lot more. Let's see, we got a couple of questions here. Is all the algebra behind this linear algebra? Yeah, that's a great way to put it. Probably about 90% of what you need to know if you want to learn the details is linear algebra. If you want to go beyond that, that would probably be like group theory and set theory. This is awesome. How do you know what a CNN architecture is best suited for the task? Yeah, so CNNs in general, it's really hard to tell which one is the best one. It really has to do with how similar the data that it was trained on is to what you're using. So say you are training your machine learning model on a bunch of numbers like this over here. You can, and it's absolutely feasible, use it for webcam data. Like that's absolutely a reasonable thing that you could do. I wouldn't suggest you do it because the data that this was trained on was black and white pictures of somebody's drawing of a number. So you can use any arbitrary model and you can use it somewhere else. That's actually true. There's nothing wrong with that. It won't work as well as you would hope, but it totally will work. That is something you can do. Now, how do you know if it's trained on something that's like more helpful? We'll see you're trying to do a computer vision task. There's this one data set called CFAR10. I think, or CI, not C, whatever, close enough, pretty close. So there's CFAR 10 and CFAR 100. And in CFAR 10 and CFAR 100, these are literally trained on 10 different or 100 different classes that if you wanted to be able to find things like automobiles, dogs, humans, ships, trucks, use CFAR 10. If you want to be able to tell if it looks like text, use something that's trained for MNIST. So basically look at what the training data was for that model, and you'll be able to pull out if it's a good idea to use it for this current system. That's not always true. It's just a really good approximation. Used to teach a machine to be good at games like chess or similar? Yes, absolutely. So there are all sorts of functions that do that. Reinforcement. Reinforcement learning. And this is exactly what we were just talking about, but like another step above that. So let's take a quick picture and look at what this all is. Actually, this is probably a good one right here. So we have our agent on the side. In this agent, don't worry about the rest of the picture, right? So we have this agent. This is very similar to what we just were talking about. It has its neural network inside of it. It's got its memory. So these three things are what we've been looking at. Exploratory, we don't have. Filters, we don't have. An algorithm, we don't have. We'll ignore that for a second. We will then take, instead of it assuming this to be like 0, and 0 meaning something, just random, like it's the letter 0. 0 could quite literally mean move forward. So action, and then the environment. Say we're playing a game like StarCraft. So there's this really awesome tool called Alpha Star. No, not Alpha Star Academy. That's not what I was looking for. Alpha Star, which is Google's solution to StarCraft 2 using the same solution that solved Go. So AlphaGo, which is a much more well-known project, is the project that beat Lee Sedol, or I believe that's what his name was, in a machine learning tool that beat somebody in Go for the first time in like forever, like a grand champion. And what this did is it literally took in the raw data of the pictures and transformed it into data that can be read on the board. There was also this other version, AlphaGo 0, which actually technically nobody knows exactly what it's doing because it got only the picture of the data and no information as to how to play the game. And it was able to learn how to play the game better than AlphaGo. There's also this other concept called Alpha Star, which is based off of both of those other two. So those two like did really well and got some amazing results. Then Alpha Star came out and they're like, hey, we can like have teams of people working together. And how do all these things work? They use reinforcement learning. And reinforcement learning basically says we have the same model we just started with. That goes in, it does something to the environment. We see if it was a good thing or a bad thing, and then we train it like that moving forward. So this is your training loop. And then as you go forward and you do better and better, you know that it's going to do better because you're training it and you're telling it it's better, and its whole goal is to do well. So yes, you absolutely can do that. There's also some really funny things like Super Mario. What's it called? Machine learning. I think it was a genetic algorithm. So there's also really interesting stuff. Yep, this is the video. There's also really interesting stuff where people have attempted to basically use genetic algorithms, which is yet another solution inside of the machine learning space. All right, this is a weird video of this, but yet another one inside of the machine learning space to be able to figure out what it is that it's looking at on the screen, what buttons it should press, and how to build a model that would then be able to do that. So it's now basically seeing what's on the screen, and the fly guy right here, that's the little black dot right here on this screen. So you can see it inside of the learning model. And you can actually watch this model kind of try to figure out what the hell it is that is going on in front of it. And this is the first of its generation. So if we go like way farther down, so this is like species 31, genome 13. So we're talking like at least 15 different iterations or 30 different iterations later. we have this thing that's able to do a lot better of a job. And then if we get to the very, very end of this, we're doing like all sorts of different like groups later. Okay, come on, let's show one more. It doesn't want to show one more? Okay, cool, whatever. So you get to like the very end of this, and it's now got this crazy, like it's spin jumping, it's doing all these things that as a human, I mean, I would never play this way. Like that is like an intense way to play. But as a computer, honestly, why wouldn't you play this way? If you could literally click every single time the exact same way, you could get some very crazy results. So to answer your question, is it possible to play games? Is it possible to do all these things? Absolutely. Let's take one more interesting step and ask the question of what else can you do with these things? So let's see if I can get a good example of this off the top of my head. So you can use machine learning on pictures always, but you can always also basically say, how do you take something random and turn it into a picture? So let's do FFT to picture. So I don't know if you guys know what an FFT is, but a FFT is the approximation of the sound wave that's coming out of my mouth right now. So I can actually give you an example of what this means. Processing. Let me just pull this up really quick because this is actually kind of fun. This lets you guys see that everything you learned so far can not only just be used for pictures, but actually could also be used for sound. It can be used for anything, literally anything. It doesn't matter. Processing FFT. Okay, cool. So this is a little project that I have that I actually use when streaming. What this does is it does a pull in your microphone data and throw it through a FFT. That FFT is going to be 8 bands wide. And then it will basically take that data, do some statistics on it, and throw it into a OSC pipeline. OSC, don't worry about it. It's a WebSocket. We're just throwing this data somewhere. But what is cool about it, and what I want to show you guys, is this part right here, the print line of what the FFT result looks like. Whew. All right, so here we go. We've got all this data spamming our console. Let's not look at the main one. Let's just look at this smaller console. The smaller console is a little bit easier to look at. Okay, so if for some weird reason I'm quiet for a second, I'm never quiet, so that's why it's weird. But if I'm quiet for a second, you'll notice all these numbers go close to 0. Now, when I start talking, you'll notice that we start getting all these jumping around and like bouncing of the numbers. So what this is quite literally doing is it's taking a sample of the sound coming out from my voice at any one like clock, at any 1 second. I think this is going at 15 or 30 frames per second. I don't remember. I think I said it 15. Yeah, 15 frames per second. So 15 times every second, it's going through and it's sampling what my voice sounds like. And it's giving us this like block of what these things are. And then from that, actually, what I personally do from it is I spawn enemies based off of this data. Because why not spawn an enemy based off of your voice? And I actually use a machine learning tool to tell if my voice has gotten beyond a certain threshold and if I'm saying certain things. So like you can do very interesting things. I don't want to say the exact hot words, but if you have a device or a G device at your house right now, you could say, hey, G device or a device. The way they do those hot words is very much so exactly what you're seeing right now, where it takes a sampling of the data, it takes that over some amount of time, it feeds that through a machine learning model, not this one, through a, actually probably like this one over here, through a machine learning model, and that machine learning model separates it out into its different possible classes, and at the end of the day, it breaks it up into, did you say this or did you say that? And now I'd say that you guys have a pretty like sprawling, like you really need to look into this stuff more if you want to use it, but you have a very nice sprawling understanding of all of this. And I'd actually say I'm kind of interested to see if you guys have any more questions overall, because I think that this is the, without going too deep into anything else, I think this is as far as I can go, because we have like, I'm just going to guess 3 minutes left before people will really want to leave. Ooh, quick water. But yeah, hopefully that made sense. I hope it was at least fun. And find me over here to be able to ask questions in a way that's not like my personal data. That's my Twitch account. You can find me live most days after like 8 o'clock when I get off of work. And a lot of the time we're playing video games using machine learning to be able to grab data from chat to basically do AFK games because I'm too lazy to let the chat like force me to do stuff directly.